You are going to travel through the universe at the speed of light, not just watch it from a distance, but feel what it is like to ride on light itself, to surf the very limit of what can ever be seen. The moment you begin, you are already inside something very special. You are inside your observable universe. You blink, and as you accelerate to light speed, the solar system falls behind you almost immediately. The planets smear into streaks of light. The sun shrinks to a bright point, then to just another star among billions. You are still in the Milky Way galaxy, but even at the speed of light it feels enormous, a vast city of stars with you racing through one of its spiral arms. As you move, you notice a strange fact. Looking ahead is like looking back in time. The light reaching you from nearby stars left a few years ago. Light from distant regions of the galaxy left thousands of years ago. You are discovering one of the deepest truths in cosmology. Every step you take at this speed is not just a journey through distance, it is a journey through the past. Now you leave the Milky Way galaxy behind. You look back and see it as a glowing spiral island of hundreds of billions of stars. Ahead of you, more galaxies appear, some small and faint, some giant and bright. You are now moving through what astronomers call the large-scale universe. On these scales, galaxies are like grains of sand. You start to notice that in every direction you look, the universe seems statistically similar. There are clusters, filaments, and huge dark voids, but the overall pattern repeats. This is what scientists mean when they say the universe is isotropic. On large scales, it looks the same in every direction. At this point, you might ask a very natural question. If you are racing through all of this at the speed of light, is there any limit to how far you can go and still receive new information from the universe? The answer is yes, and that limit is exactly what defines your observable universe. The observable universe is the region of space from which light has had time to reach you since the beginning of cosmic time. It is not the entire universe. It is just the portion that has had enough time to send you a signal. To feel this, imagine pausing for a moment in the middle of deep intergalactic space. You stop moving relative to the distant galaxies and simply let light come to you from all directions. Around you there is an invisible sphere, not of matter, but of information. Inside that sphere, light has already arrived, carrying images of galaxies, nebulae, and ancient events. Outside that sphere, there are regions whose light is still on the way or will never arrive at all. The radius of this sphere is the radius of your observable universe. You are exactly at its center, not because your position is special in the universe, but because the concept is defined around the observer. Now take off again at light speed. As you rush outward, you cross shells of older and older light. Nearby galaxies show you the recent universe. Farther out, you see galaxies as they were billions of years ago. If you continue, you eventually approach the most distant light we can detect. This is not from stars or galaxies. It is the cosmic microwave background, the faint afterglow of the early universe. That light was released when the universe was only about 380,000 years old. For all the time since then, it has been traveling through expanding space, slowly stretching into microwave wavelengths. When you finally reach that shell of light in your mind, you are touching the edge of visibility itself. There is no older light that can reach you from before that moment, because before that, the universe was so hot and dense that light could not travel freely. Here is where the speed of light becomes more than just a number. It becomes a cosmic rule that sets a hard boundary. Nothing can travel faster than light. No signal, no particle, no piece of information can outrun it. This means there is a maximum distance from which light could have reached you in the age of the universe. That distance defines what is called the particle horizon. You can think of it as the ultimate edge of your observable universe. Not a physical wall, but a limit on what can ever be known. Anything beyond that horizon is part of the universe, but forever beyond your ability to observe. The light from those regions has not had time to reach you, and in many cases, because of the expansion of space, it never will. Notice how odd this feels. You are traveling at the speed of light, the fastest speed allowed by nature, and yet there are regions you can never see. You could aim straight at them for as long as the universe exists, and their light would still never catch up. This is because space itself is expanding. On the largest scales, galaxies are being carried away from each other by the stretching of space. Some are receding so quickly that their effective distance from you grows faster than light can close the gap. Their present and their future are sealed off from your view. But there is another twist. Even though there is an ultimate horizon, your observable universe is not static. As time passes, more light from more distant regions reaches you. The radius of your observable universe increases. It is like standing next to a pond in the dark with a small ring of lanterns slowly turning on farther and farther away. Every minute, more of the shore becomes visible. In the same way, with every passing moment, your cosmic bubble of information becomes slightly larger, even if you do nothing at all. Now picture this from a different vantage point. Somewhere else in the universe, unimaginably far away, another observer is performing the same thought experiment. For them, their observable universe is also a sphere centered on their position. They see galaxies arranged in a way that looks statistically similar to yours, but the details are different. Some galaxies that you can see are beyond their horizon. Some galaxies that they can see are beyond yours. The underlying universe might be far larger than both spheres combined, possibly even infinite, but each observer is limited to their own bubble. This leads to an important idea that will connect directly to the next parts of your journey. When you eventually ask how big your observable universe is in numbers, you will find that its radius is about 46.5 billion light-years, even though the universe is only 13.8 billion years old. That difference will only make sense when you combine everything you have just felt with an understanding of expanding space and stretched distances. The distance to where the light came from is not the same as the time the light travelled. Space grew underneath the light as it moved. So for now, hold on to this experience. You travelled at the speed of light. You saw that every direction is a look into the past. You discovered that there is a cosmic bubble around you defined entirely by the age of the universe and the speed of light. Inside that bubble lies everything you can ever observe. Outside, it lies a vast unknown you will never be able to touch. In the next part of this story, you will put numbers on this bubble, explore why its radius is tens of billions of light years, and see how the stretching of space turns your journey into something even more mind-bending than simple distance. You discover that you live inside a cosmic bubble, a sphere of visibility defined by how far light has had time to travel since the universe began. That bubble is your observable universe. Now it is time to ask a question your brain will resist at first. How big is this thing really? Not in vague words like vast or enormous, but in actual numbers that you can try to wrap your mind around. So imagine you are still travelling at the speed of light, starting from Earth. A year passes for you as a beam of light. You are now 1 light year away. Keep going. After 10 years, you are 10 light years away, out past our local neighbourhood of stars. After 1,000,000 years, you have left the Milky Way galaxy far behind. You have crossed the space between galaxies and are drifting through intergalactic darkness. The scale is already beyond anything in normal life, but you are nowhere near the edge of your observable universe yet. If you let 13.8 billion years pass on your cosmic odometer, you might expect to be at the edge, because that is the age of the universe. Light has had 13.8 billion years to travel, so should the radius of the observable universe be 13.8 billion light years. This is the first big shock. It is not. The radius of your observable universe is about 46.5 billion light years. Its diameter is roughly 93 billion light years. That means if you could somehow freeze the universe right now and measure the distance from one side of your observable bubble straight through you to the other side, you would get about 93 billion light years. So why does the light travel time, 13.8 billion years, not match the present distance, 46.5 billion light years? The answer is hidden in the medium you are travelling through. Space is not a rigid stage, it stretches. While the light has been moving toward you, the space in between has been expanding. This means the galaxy that emitted the light you are just receiving now is much farther away today than the distance the light actually travelled through. The path of the photon, measured as time times speed, gives you the light travel distance about 13.8 billion light years. But the comoving distance to the source, The distance right now, if you could measure it at this instant, is around 46 billion light years. The difference is not because light sped up. Light always travels at the same speed in a vacuum. The difference exists because the fabric of space has been stretching under its feet. To see this more clearly, imagine you are running on one of those moving walkways in an airport, but the walkway itself is slowly stretching as you move. You cover a certain distance with your feet, but the distance between your starting point and the place you are trying to reach becomes larger while you are moving. On cosmic scales, that stretching is the expansion of the universe. When you, as a beam of light, head toward Earth from a distant galaxy, you are indeed moving at the speed of light, but the underlying space keeps expanding, so the present separation is larger than speed multiplied by time. This is why cosmologists are very careful about what distance they mean. The light travel distance, also called look-back time distance, is how long the light has been in flight. The current proper distance is how far away the source galaxy is now in the expanding universe. When we say the radius of the observable universe is about 46.5 billion light-years, we are talking about that present proper distance. When we say the light has been travelling for 13.8 billion years, that is the look-back time. Both descriptions are true, they are just answering different questions. As you continue your journey at light speed, you eventually reach the oldest light you can possibly see, the cosmic microwave background. This faint glow comes from a time when the universe was about 380,000 years old. Before that, the universe was so hot and dense that it was opaque, like a glowing fog of ionized plasma. Photons could not travel freely because they were constantly scattered by charged particles. When the universe cooled enough, protons and electrons combined into neutral atoms, and suddenly light could stream through space. That first freely traveling light is what you see as the cosmic microwave background today. It has been traveling for almost the entire age of the universe, redshifted from visible and infrared wavelengths down into microwaves by cosmic expansion. Here is another subtle but important point. When you detect a photon from the cosmic microwave background, you know it has been in transit for about 13.8 billion years, minus that initial 380,000 years. But the region of space from which it was emitted is now roughly 46 billion light-years away. You are not seeing that region as it is now. You are seeing it as it was when the universe was young and hot. This is why the observable universe is truly a time machine. Every step outward in distance is also a step backward in time. Near you, you see relatively recent galaxies. At intermediate distances, galaxies are younger, bluer, more active. At the very edge, you no longer see galaxies at all. You see a uniform glow with tiny temperature variations, the fossil imprint of the early universe. The volume of the observable universe, given a radius of about 46.5 billion light-years, is on the order of 10 to the power of 80 cubic meters. That is a number so large, it refuses to become intuitive. If you imagine each cubic meter as a box you could hold in your hands, you would need more boxes than there are atoms in all the stars you can see to fill that space. Yet, astonishingly, the average density of matter in that volume is extremely low, only a few hydrogen atoms per cubic meter. Most of what fills that huge volume is not stars and galaxies, but almost empty space. By now, as you race across these scales in your mind, you might feel a tension. On the one hand, the observable universe is staggeringly large, tens of billions of light-years in radius, volumes of 10 to the power of 80 cubic meters. On the other hand, what you are seeing is still only a bubble, a finite piece of something potentially much larger. The boundary of what you can observe is set by the age of the universe and the expansion of space, not by the true edge of existence. For all current evidence suggests, the universe beyond your horizon simply continues with roughly the same properties, possibly without end. Keep that feeling of disorientation close, because it is exactly what cosmology wrestles with. You are limited to a finite sphere of information, yet within that sphere the numbers are already beyond comprehension, and you have only talked about size and distance so far. You have not even asked what fills this bubble, how many galaxies it contains, how many stars, how much matter, and what mysterious ingredients make up most of its energy. In the next part of this journey, You will fly through that volume and start counting. You will see how many galaxies live inside your 93 billion light-year wide bubble, what they are made of, and why most of the universe is not the kind of matter you are familiar with at all. You are still flying through your 93 billion light-year wide bubble, riding at the speed of light, but now you are going to stop thinking just about size and start asking a much more intimate question. What is actually inside this thing? If your observable universe is a gigantic cosmic container, what does it contain? How many galaxies? How many stars? How much matter? And maybe the strangest part of all, how much of it is the kind of matter you are made of? So imagine you slow down just enough to look around. At first you notice the obvious. Galaxies. Everywhere. Spirals, ellipticals, irregular shapes, some tiny and faint, some gigantic and blazing. When astronomers map the observable universe using surveys like the Hubble Deep Field and larger ground-based projects, and then extrapolate across the full sky, they estimate that there may be up to about 2 trillion galaxies inside your observable universe. That is 2 trillion island universes, each with its own history, its own stars, planets, black holes, and possibly its own observers, wondering about the same questions you are asking right now. Now pick one galaxy and dive in. A typical galaxy like the Milky Way contains hundreds of billions of stars. Some monster galaxies contain over 1 trillion stars on their own. Multiply that by up to 2 trillion galaxies, and you get a total number of stars that can easily exceed 10 to the power of 24. That is one followed by 24 zeros. People sometimes say there are more stars in the observable universe than grains of sand on all the beaches on Earth. Surprisingly, that comparison is roughly in the right ballpark. You are living in a universe where stars are as common at cosmic scales as sand grains are on a shoreline. But stars are only one way for matter to arrange itself. A lot of the ordinary matter is floating around as gas in and between galaxies, or locked up in planets, dust and cold clouds. When cosmologists talk about ordinary matter, they usually mean baryonic matter, the kind made of protons, neutrons and electrons, the stuff that builds atoms and molecules. All the stars, planets, nebulae, gas clouds, and you yourself are part of this category. You might think that this familiar matter would dominate the universe. After all, it is everything you can see and touch. But when scientists measure how much matter and energy the universe contains, using observations of the cosmic microwave background, galaxy clustering, and distant supernova, they find something deeply counterintuitive. Ordinary baryonic matter makes up only about 4.8% of the total energy content of the universe. Dark matter contributes about 26.8%. Dark energy takes the biggest slice, around 68.3%. In other words, everything you have ever interacted with, every atom in your body, every star that has ever shone, is just a thin layer of frosting on a much larger cosmic cake, dominated by invisible ingredients. Dark matter does not emit or absorb light, but its gravity shapes the rotation curves of galaxies and the way light bends around galaxy clusters. Dark energy acts like a kind of negative pressure built into space itself, driving the accelerated expansion of the universe. Now, keep moving at light speed and imagine that if you could somehow weigh all the ordinary matter inside your observable universe, you would get a number of around 1.5 times 10 to the power of 53 kilograms. That is the combined mass of all the atoms in all the stars, gas clouds, planets, and everything else made of baryons within your cosmic bubble. If you convert that mass into a count of individual atoms, you end up with roughly 10 to the power of 80 atoms. This estimate is sometimes called the Eddington number. It is the number of particles that make up all of the ordinary matter in your observable universe. Every proton in every star, every neutron in every heavy element, every particle in your body is one of those unimaginably many building blocks. Here's the twist that really challenges your intuition. Even with all those atoms, all those galaxies, all those stars, the universe is mostly empty. On average, there are only around 5 hydrogen atoms per cubic meter of space. Picture a box 1 meter on a side. In the air around you, that box would contain a huge number of molecules. Out in intergalactic space, that same box might contain only a handful of atoms, or even less. When you zoom out enough, matter looks like a faint mist stretched across an enormous volume. Yet that mist is not spread uniformly. As you race through your observable universe, you see that matter has arranged itself into a vast cosmic web. Galaxies are gathered into clusters. Clusters link into filaments, and between those filaments are enormous voids where there are very few galaxies at all. On the largest scales, this web looks like a three-dimensional network of bright threads and dark holes. Simulations of structure formation in a universe filled with dark matter and dark energy reproduce this pattern beautifully, showing that gravity slowly pulled matter into these filaments over billions of years, while dark energy pushed space itself to expand faster and faster. If you follow one of those filaments, you can pass through groups of galaxies, then clusters, then superclusters, huge associations of many clusters bound together by gravity. But beyond the scale of superclusters, the pattern begins to fade into statistical randomness. On those giant scales, the universe becomes homogeneous, meaning that its properties are nearly the same in every region when averaged over large enough volumes. This is part of why cosmologists can talk meaningfully about the average density of the universe and its overall composition. The details are messy, but the big picture is surprisingly smooth. As you move through this web at light speed, you might start to feel a shift in perspective. When you began, you might have thought of yourself as a small thing in a big universe. Now you realize that you are also made of the same atoms, part of the same tiny 4.8% of ordinary matter that forms stars and galaxies. You are made from the rare stuff, the luminous dust in a sea of dark matter and dark energy. You are literally built from atoms that once floated in interstellar gas, collapsed into stars, fused into heavier elements, exploded, and then reassembled into planets and life. And yet, for all the detail you can now picture inside your observable universe, you have only described what is within the bubble you can see. All those galaxies, all those stars, all those atoms share a deeper limitation. They are part of the region that can exchange light with you. Beyond that region, the universe may continue with similar filaments, clusters, and voids, filled with even more galaxies and even more matter, but those will never appear in your sky. Your cosmic web is just one patch in a larger tapestry you will never fully view. In the next part of this journey, your role in this story is going to change again. You will stop just counting what is inside your observable universe and start asking what its future looks like. How will this web evolve as dark energy keeps pushing space apart? Which galaxies will remain visible and which will drift beyond your horizon forever? And what does it really mean that the observable universe is not the same as the reachable universe? As you keep riding the speed of light into the far future, you will see entire galaxies fade away, horizons appear that no amount of waiting can cross, and you will confront the unsettling idea that most of the universe will always be out of reach no matter how advanced any civilization becomes. Now, you're going to do something even stranger. You're going to travel into the future and watch what happens to your observable universe as time goes on, as expansion accelerates, and as entire regions slowly slide out of your reach. So imagine this. You pause in the middle of intergalactic space, far from any particular galaxy. Around you stretches the cosmic web you have just explored, filled with clusters, filaments, and vast dark voids. Now you let time run forward, faster and faster, while you continue to feel what light is doing. One of the most important discoveries in modern cosmology is that the expansion of the universe is not slowing down under gravity. It is accelerating because of dark energy. That means distant galaxies are not just drifting away. They are being carried away faster and faster as space stretches. At first, not much seems different. Nearby galaxies in your local group move only slowly relative to you. Gravity still matters strongly here and keeps them bound together. But as you look farther out, you see that many galaxies are receding from you at very high effective speeds. Some of them are already moving away faster than light, not because they are breaking the cosmic speed limit, but because the space between you and them is stretching so quickly that the distance grows faster than light can close the gap. The rule that nothing can move through space faster than light is still safe, but space itself is not bound by that rule. Now start to think in terms of horizons again. Earlier you met the particle horizon, the limit set by how far light has had time to travel since the beginning of the universe. But there is another, more subtle boundary that has to do with the future. Some of the light that distant galaxies are emitting right now will never reach you, no matter how long you wait. Those galaxies are crossing what is called a cosmic event horizon. Beyond that horizon, their future light is lost to you forever. It is as if they fall over a waterfall at the edge of visibility while you remain upstream. If you were to mark out that future visibility limit in terms of distance, it lies at around 62 billion light-years for an observer like you in a universe dominated by dark energy. Galaxies that are currently beyond that distance are already permanently unreachable, even in principle, because the expansion is carrying them away too quickly. Some galaxies that are closer than that limit today will cross it in the future as the expansion continues to accelerate. From your perspective, those galaxies will slowly become fainter and redder as their light is stretched to longer wavelengths. Over enormous spans of time, they will redshift so much that their light becomes undetectable and they effectively fade from your observable universe. This is one of the most sobering consequences of an accelerating universe. Even though your observable universe might continue to grow in the sense that more ancient light reaches you from just inside the particle horizon, the set of objects that can ever send you new signals is shrinking. The reachable universe, the region from which a signal sent now or in the future can ever get to you, is much smaller than the full observable universe. Observable does not mean reachable. There are galaxies you can see today whose current light is arriving, but any light they emit from now on will never make it to you. Let time run even faster in your mind. Stars burn their fuel and die. New stars form from gas clouds, but the overall rate of star formation in galaxies declines. Many galaxies use up or lose most of their cold gas. The bright young blue stars become rarer. The universe slowly shifts toward older, redder populations of stars. At the same time, dark energy keeps doing its quiet work, driving galaxies farther and farther apart on large scales. From your vantage point, riding the speed of light and watching the sky change over trillions of years, more and more distant galaxies slip beyond your event horizon and disappear. Their light stretches into radio waves and then into wavelengths so long they are practically impossible to detect. Eventually, only the galaxies that are gravitationally bound to your local region remain visible. In our case, that means the local group and the larger Virgo supercluster scale that may collapse into a single huge structure. Everything beyond that will be carried away by expansion faster than light can follow. In that far future, an observer in a galaxy, like the merged remnant of our local region, would look up and see a very different sky. There would be stars in their own galaxy, and maybe a few small companions, but no visible distant galaxies at all. The cosmic microwave background, which today is a clear piece of evidence for the Big Bang and the hot early universe, would have redshifted so much that it would be effectively undetectable against any local noise. The clues that told you about the true scale and history of the universe would be gone. Future astronomers in that isolated island of matter might conclude that their galaxy is all there is, unaware of the once visible web of galaxies beyond. Think about what this means for you now. You live at a special time from a scientific perspective, a time when galaxies are still visible over vast distances, when the cosmic microwave background can still be measured, when the expansion history of the universe can still be read from the sky. You exist at a moment when it is still possible to piece together that dark energy is real, that the expansion is accelerating, and that horizons limit what is observable and what is reachable. As you continue to ride light into this imagined future, another question appears. If the reachable universe is so much smaller than the observable one, what does that say about the ultimate fate of structures, of information, of any civilization that might try to explore? Even with the most advanced technology, no one will ever visit most of the galaxies you see. They are already behind a horizon that cannot be crossed. The universe, on the largest scales, is slowly dividing into isolated regions that can never communicate with one another. In the very distant future, over unimaginably long timescales, stars will exhaust their fuel, stellar remnants will cool, and black holes will slowly evaporate through Hawking radiation. The universe will become colder and emptier. But the key idea for your story right now is this. What you see when you look at the sky today is almost certainly only a tiny fraction of the total universe. And even within that fraction, there is a smaller core that you can ever influence or reach. So you began this journey standing under a dark sky, wondering how far you could see. You learned that you live inside an observable universe, a cosmic bubble defined by light and time. You discovered that its radius is around 46.5 billion light years, that its diameter is about 93 billion light years, and that the light you see is a record of the past, not a snapshot of now. You flew through that volume and saw up to 2 trillion galaxies, more stars than grains of sand on Earth, and a composition dominated not by the matter you know, but by dark matter and dark energy. And now, in part 4, you have watched that same universe evolve into the far future, where horizons sharpen, galaxies fade away, and only a small island of matter remains visible. The question you're left with is not just how big the universe is, or what it contains, but what it means to live inside a cosmos where so much will always lie beyond your reach. In a universe with horizons, curiosity itself becomes something powerful. You have this brief cosmic moment where the sky still tells the full story. What you do with that knowledge, how far you push your understanding, and how well you preserve it for those who come after, may be one of the most important parts of your role in this vast, accelerating, and mostly invisible universe.